Hello everyone, Chris here. A few weeks ago, after a long discussion, one of those late night talks that starts with physics and somehow end up sounding like philosophy, I walked out of a small event in New York. Not a big conference, more like a room with a whiteboard, coffee that's been reheated twice. And people who argue with patience because they genuinely care. And someone said something that sounds almost offensive in its simplicity. So what do you actually believe in is real? Not what's useful, not what's measurable, not what's practical. Just real. I gave the kind of answer you give when you're buying time. Something about experiments, about equations, about evidence. But on the way home, that question kept me following me. Because the uncomfortable truth is as a reality is obvious. The floor beneath your feet feels solid, right? The air feels empty. Time feels like it flows. Steady one way, like a river. And yet, if you ask modern physics what the world is made of, it gives you a reply that is both beautiful and disturbing. What your sense calls solid is not solid in the way you imagine. What feels like nothing is not nothing. And what you call matter is not a set of little hard objects. Our brain was built to reveal the ultimate structure of nature. It's a biological survival machine. Your ancestors did not need to know that atoms are mostly empty space. They needed to know one thing. Can I eat this? Will this kill me? Or can I run fast enough? So evolution gave us a user interface, a simplified dashboard. Just like your computer doesn't show your transistors, voltage, or electronic flows, it shows you icons, a folder, photo, file, and you trust those icons because they work. In the same way, your mind shows you a table, tree, person. These are not lies, they are shortcuts. They are the brain's way of compressing a universe that's far too deep for raw perception. So today, I don't want to explain physics in a usual way. I want to do something else. I want to take that question, what's real, seriously, and want to show you why the first thing we have to draw in the naive picture of matter as a tiny solid things. Because once that picture breaks, everything else starts to make sense. In school, we were shown atoms like tiny solar systems. A nucleus in the middle and little electron marbles orbiting around it. Let's throw that image away. It's outdated. And it's deeply misleading. In modern physics, especially in quantum field theory, there is no fundamental place for the idea of perfectly solid particles. As a tiny billiard ball, the standard model is not really a theory of little objects moving through empty space. It's theory of fields and their interactions. And it's built on symmetry. Now picture an invisible ocean. It fills the entire universe. It's here in your room, inside your body, out in deep space. That ocean is a field, and every particle type has its own field. An electron field, an quark field, electromagnetic field. But let's make this precise without losing the intuition, right? A field is not poetry. It's a physical quantity defined at every point in space and time, like temperature in your room or the electric field around a charge. Quantum field theory goes further. It says the field itself is fundamental, and we quantize the field, meaning energy in the field comes in discrete chunks. Those chunks have a name, we call them quanta, and a particle is a quantum of a field. So when a field is calm, it's lowest energy state. You don't see tiny objects flying around. But when the field gets a localized packet of energy, when it's excited, the theory predicts a one quantum state with a definite properties: mass, charge, spin. That's what we call a particle. An electron is an excitation of the direct electron field. A photon is an excitation of the electromagnetic gauge field. Quarks are excitation of quark fields held together by the gluon field. In quantum chromodynamics, so yes, particle is real, but it's not a little hard bead. It's the way a field allows up in an experiment. Now you might say, wait, but detectors show particles. Cloud chambers show tracks. Photodetectors make clicks. Exactly. Detectors register localized events because, and QFT explains this, because interaction are local and energy is observed in discrete quanta, and particle is now the field announces itself when it trades energy with matter. Now look at your hands. They feel dense, they feel solid, but in reality they are stable structures made from many fields at once. So why does this world feel solid? Not because matter is made of tiny hard bits, right? It feels solid because of two deeply physical effects. First, electromagnetic repulsion. The electron in our atoms and the electrons in the table don't calmly overlap. And second, the Pauli Exclusion Principle. Fermions, like electrons, cannot pile into the same quantum state. This is not a force in usual sense, right? It's a structural rule built into the mathematics of fermionic field. And it's one reason matter has stiffness, volume, and stability. So solidity is not fundamental. Solidity is an emergent effect of fields interacting and quantum statistics doing their job. And here is the final shift. In QFT, fields are not things sitting inside space, like furniture in your room. Fields are part of deepest description of what the room is. Space is not a passive emptiness. It's the arena where fields existing and interact. And what we call matter is a stable, repeatable pattern inside your system. You are not a pile of matter, marbles. You are an organized pattern in a universe of fields and standing waves stable enough to remember to think, to ask questions inside an ocean that never stops moving. So let's go one step deeper. If what we call a particle is really an excitation of field, then the next question is simple. Where is it? In everyday life, location is a fact. The key are on the table, right? In quantum physics, where is often not a single fact. You can point to it in advance. What you have is a description of possible outcomes and how likely they are. At the core of the theory is something called a quantum state. Not a picture, not a tiny object with a hidden path. A state is a mathematical object that encodes what can be predicted. Physicists write as a C. And here is the key idea. The state is not in space. The way a chair is in space. It's more like a rule book for what space we will give you when you interact with system. Now, superposition. People say it's in two places at once, but the clean meaning is the state cannot be written as a mixture of alternatives, a linear combination. Not classical, certainly, like we just don't know, but multiple possibilities coexisting inside the description. And quantum theory doesn't start with ordinary probabilities. It starts with probability amplitudes. Amplitudes have size and phase. That phase is not decoration. It's why quantum system can interfere. Then comes the rule that turns amplitudes inside actual statistics. The chance of an outcome equals the square of the amplitude magnitude. That's why quantum mechanics is both precise and unpredictable. You can predict distributions extremely well, but not a single outcome in general. This is why the coin analogy is only half true. A flying coin is already either heads or tails. We just don't see it yet. In a truly quantum experiment, a single photon in an interferometer or an electron spin, the theory itself does not assign a definite classical answer in advance. Is it assigns amplitudes. Now, what is measurement? In physics, measurable quantities are called observables, and observables are represented by operators. When you measure, you don't get anything. You get one of the allowed value. One of the permitted outcomes. And after that, the state updates to match the new information. People call this collapse. A careful way to say it, it's measurement is an interaction that produces a definite recorded result. And the state is updated, conditioned on that result. Here is another key point. Quantum theory has two kinds of change. Between measurements, the state evolves smoothly and predictably, according to a strict dynamic law. But when a definite outcome is recorded, the update is not smooth. It's probabilistic. That split smooth evolution plus probabilistic outcomes and is one of the deepest sources of quantum fog feeling. So why don't we see this fog in our daily life? Because quantum coherence is fragile. When a system interacts strongly with an environment, the delicate phase relationships and they get scrambled. Interference disappears, not because the world becomes less quantum, but because the information gets spread out into environment. That's why chairs don't behave like smeared probabilities waves. The quantum description is still there underneath, but the interface is gone, and what remains look classical. One more consequence: some properties cannot be perfectly sharp at the same time, not because our instruments are weak, but because the mathematical objects representing those properties don't allow it. And so universe is not a chaos. It's a rule-driven, extremely lawful thing. But the outcomes, it gives us the fundamental probabilistic. Reality is not a pre-written list of facts. It's a generator, a precise engine of possibilities that becomes definite, where interactions leave stable records in the world. We have talked about a world made of quantum state and probabilities. Now we hit the part that sounds like science fiction, but in routine, it's real, it works in real laboratories. Entanglement and quantum teleportation. First, entanglement. What is it exactly? Two systems become entangled when they share a single joint quantum state that cannot be split in two independent pieces. Meaning, you cannot write the full state as this is A times this is B. Not two separate stories, only one combined story. Physicists call this a non-separable state. And this is where the weird correlations appear. If you measure system A, you get a random outcome. If you measure system B, you also get a random outcome. But when you compare these results, you find correlations that are too strong to be explained by a classical model based on local hidden variables. This is not just philosophy. This is a statement, tested many times in experiments, different experiments. There is a whole class of tests, called Bell tests. They check whether nature can be explained by local realism. Local meaning no influences faster than light. Realism meaning outcomes were fixed in advance. Quantum mechanics predicts violations of Bell in collates. And experiments observe these violations. So the universe refuses to behave like classical common sense. Now people often say, if you change one particle, then another changes instantly. That sentence is a little bit dangerous. Here is the more careful version. Entanglement creates correlations that show up when results are compared. But it does not let you send a controllable message faster than light, of course. That limit is called the non-signaling principle. No matter what you do locally, the other side does not receive a useful instant signal. Relativity stays safe. So, what did Einstein mean by spooky action at a distance? He meant the correlations themselves feel non-classical. They don't fit the classical idea of independent objects in space. It's as if the two systems behave like one distributed object with parts separated in space. Second interesting thing is teleportation. This is the moment where people imagine Star Trek beams and bodies dissolving and so on. That's not what is it, of course. Quantum teleportation does not move matter. It does not transport energy. It transfers a quantum state. A state from one system to another distant system. And the mechanism is precise. It needs two ingredients. One, a shared entangled pair. Two, an ordinary classical message. Here is core setup. You have an unknown quantum state you want to transfer. Call it this state. You also share an entangled pair with a distant partner. One half is with you, one half is far away. Now comes the key step. You perform a joint measurement on two things at once. The unknown state and the you half of entangled pair. This is not a normal measurement of each object separately. It's a combined measurement in a special basis called Bell basis. This measurement produces a definite classical result. In a practice, it's like getting two classical bits of information, one of four possible outcomes. Those two bits are ordinary. You can write them down, of course. You can send them over the internet, you can transmit them by radio, and that classical message is limited by the speed of light, of course. Now, on the distance side, your partner uses these two bits to perform a simple correction operation on their half of the entangled pair. A small unitary tweak, a rotation, a flip, a phase change. And after that correction, the distant system becomes the exactly same quantum state that you started with. Not approximately, the same state. And an important detail is the original state does not remain with you. Teleportation does not copy, it transfers. That's not a loophole. It's a deep rule of quantum physics. You cannot make a perfect copy of an unknown quantum state. That is called non-cloning theorem. Teleportation respects this, of course. The state moves, but it does not duplicate. So what do we do with teleportation, right? It's already used as a building block for quantum networks, for connection distance nodes, for extending entangled across large distances, for protocols that will eventually power quantum communication infrastructure. And now the philosophical punch. If you could do this with not a photon, but with every quantum detail that makes you, would this result still be you? Or would it be a perfect physical continuation with a different story of identity? Physics doesn't answer that for free, but it forces a question: are we fundamentally stuff or are we fundamentally pattern? Information embodied in a matter and fields. Entanglement and teleportation doesn't just stretch our technology. They stretch our intuition about what it even means to be separate objects in space. And that's why this is not science fiction. It's a mirror. Hold up to reality, showing us that the universe is stranger that our senses ever prepared us for. When you peel away everything your senses give you: color, smell, hardness, even the idea of stuff. What's left isn't a picture, it's structure. And the language of this structure is mathematics. We usually think math is something humans invented, a tool, a convenient way to describe nature. But physics keeps pushing us toward a stranger conclusion. Math is not just a description. It often looks like a blueprint. Here is what I mean. In physics, we don't start by asking, what do I feel? We start by asking, what stays the same when I change my point of view? That idea has a name: symmetry. A symmetry means you transform something, shift it, rotate it, speed it up, and the core rules don't change. And here is the shock. Symmetry is not just aesthetic, it's productive. And it creates laws. This is a deep result in physics called Noether's theorem. It links symmetries to conservation laws. If the laws don't change over time, you get conservation of energy. If the laws don't change from one place to another, you get conservation of momentum. If the laws don't care which way you rotate, you get conservation of angular momentum. So conservation laws are not just rules we discovered. They are consequences of mathematical invariance. Now let's go one layer deeper. A huge part of physics can be written in terms of something called the action. Instead of tracking every force directly, you write a single object, a recipe that summarizes the system. Physicists call it Lagrangian. And then the equation of motion comes out of one principle. The system follows the path and makes the action stationary. Not because nature thinks, but because the mathematics acts like a selection rule, like a filter. Only certain histories are allowed by the structure. And when you accept this, the world begins to look less like a machine made of parts and more like a theorem unfolding in time. Now, this is not just an abstract philosophy. There is a pattern in history of physics. Mathematics often arrives first. Reality follows. Maxwell wrote down equations for electricity and magnetism, and the equations implied waves, not as a guess, as a necessity. So those waves had a speed determined by constants in equations, and that speed matched the speed of light. So light was not discovered. to be electromagnetic by experiment first. It was predicted by the structure of math. And I like another example. Dirac wrote an equation that respected relativity and quantum rules. The math didn't just describe electrons. It demanded something extra, a mirror particle, same mass, opposite charge. At the time, it sounded absurd, and then it was found, the positron. Or take gravity. Einstein rewrote gravity not as a force, but as a geometry, curvature of space-time, a mathematical object, and the geometry predicted effects before we could properly measure them. Light bending around the sun, time running differently in gravity, waves in space-time itself. Again and again, mathematics behaves like a compass, not always perfect, but often uncannily accurate. So the uncomfortable question becomes, why? Why is nature so loyal to abstract structures? One possibility is practical. Math is simply the most compressed way to describe patterns. It's the ultimate data compression. But there is another possibility, more radical to say. Maybe the mathematics is not just our language. Maybe it's the substrate. Maybe physical reality is what mathematical consistency looks like from the inside. I'm not asking you to believe that's the dogma. I'm asking you to notice the pattern. When we dig deeper, we don't find more stuff. We find more relationships, more invariances, more structure. And that structure is mathematical, whether we like it or not. So when you see an equation in physics, don't treat it like a metaphor. Treat it like a skeleton of reality. The thing that stays when every surface illusion is stripped away. And once you accept that, the world stops looking like a pile of objects and starts looking like a coherent, self-consistent code running everywhere, all at once. Now we reach the strangest idea of all, the void. Because when most people hear vacuum, they imagine nothing, empty space, zero. But in physics, a vacuum is not nothing. A vacuum is a state. It's a lowest energy state of a set of quantum fields. Not the absence of reality, but the quietest version of it. And even that quiet is not perfectly quiet. Why? Because quantum systems cannot have everything set to zero at the same time. It's impossible. If you try to freeze a field completely with a perfect stillness, the uncertainty built into the theory pushes back. So even an absolute zero temperature, the vacuum contains 0-point fluctuations. That phrase sounds abstract, so let's anchor it. These fluctuations are not a vibe, they leave fingerprints. We can measure them. For example, the Casimir effect. Put two uncharged metal plates very close together in a vacuum. They attract, not because of static electricity, but because the allowed vacuum modes between these plates are different from the modes outside of these plates. The vacuum exerts a pressure difference that is not philosophy. This is measured force. Another interesting example, the lamp shift. Tiny shifts in atomic energy levels that match what you expect when the vacuum slightly modifies how electrons behave near a nucleus. Another interesting case, spontaneous emission. An excited atom can emit a photon even when there is no incoming light, because it's interacting with vacuum fluctuations of the electromagnetic fields. So the vacuum is not a dead stage, it's an active medium. Now people often describe this as virtual particles popping in and out. That image is really popular, but it can mislead. Here is a careful version. Virtual particles are not tiny balls, literally appearing and vanishing like fireworks. They are a way the mathematics organizes interactions, especially in perturbation theory, a bookkeeping language for how fields influence each other. But the effects can calculate with that language. Those effects are real. The vacuum also does something else that is even more dramatic. It changes what we mean by empty. In quantum field theory, the vacuum is not featureless. It can have structure, a baseline, configuration, a non-zero expectation value. And that brings us to the Higgs field. The Higgs field permeates space, and many particles interact with it. That interaction is what gives them rest mass, the kind of mass that makes slow objects possible. Without that, many particles would behave as if they were massless. And the chemistry that builds atoms would not exist in the form we know. But I want to add one more precision point, because it matters. When you look at ordinary matter, like you or a rock or table, most of the mass you feel does not come directly from Higgs. Most of it comes from strong interactions, from the energy locked inside photons and neutrons, from the binding energy of quantum chromodynamics QCD. So in a deep sense, what we call mass is in everyday life is largely energy held in stable patterns by fields and interactions. And let's make a step back and feel how strange this is. We usually think the vacuum is a background, but the vacuum is participating. It shapes forces, it shapes atoms, it shapes what a particle even means. And then there is one more unsettling fact. If the vacuum has energy and it goes, then gravity should respond to it. So you arrive at one of the biggest tensions in modern physics. What is the gravitational effect of vacuum energy? Why is it not enormous? Why is the observed cosmic value so tiny compared to what naive estimates suggest? This is tied to the cosmological constant problem. In other words, even nothing still contains one of the deepest unsolved questions in all of science. So the vacuum is not emptiness. It's the most fundamental environment we have. A restless baseline, a medium full of structure, a silence engine that makes matter possible. And that means something personal. because it flips the story. You are not a little object floating in a cold, empty void. You are a stable, self-organized pattern inside of universe, where even empty space is alive with rules, fluctuations, and fields. The void is not the absence of reality. It's one of reality's deepest form. And we exist because the vacuum has structure, and the laws let that structure build complexity. So when you say nothing, physics quietly answers. There is no such thing. There is only the lowest energy state of an infinite ocean, and these beautiful consequences of its motion. Thank you for listening. Stay curious.